Is it really though? You've got a nice little philosophical discussion. What are we doing here? We're math 21. I think this is day 10. And so this is like day lecture. And we're starting chapter 5 and should get through half of it today. Chapter 5 is on probability, and stack crunch just is not a viable option. It's not viable. The only thing you would use it for is the exact same thing you would use a basic calculator for. Calculating probabilities. But you can use a calculator as much as you want, and a cheap $8 calculator does everything we will need in this class, as you'll see. So what the hell is probability? You know, I throw that word out there. What is it? Probability. Did someone say something?
How likely it is to show up, or how likely it is for someone to choose a certain question, I guess.
It's the likelihood of an event occurring. That's the short way of saying it. That's exactly it. Probability measures the likelihood of a random event happening or occurring. Another way we say it is it is the long-term proportion in which a certain outcome is observed. So, like, it implies we don't know the outcome ahead of time. I asked this a little bit ago with the last class. Has anyone in here never used a deck of playing cards? Your good old hearts, diamonds, clubs, spades. Really, all of you have. Like, this looks familiar to everybody. Those cards look familiar to everybody. Okay. That's interesting. Like pre-pandemic, I would ask and like the chances of someone 18 or 21 or under recognizing those was about 50-50. Since the pandemic's over, like both stats classes I have right now, no one said that they didn't recognize them. So I'm thinking like some people got introduced to card games while they were stuck at home that weren't introduced before. You know what I mean?
I'm old enough to play solitaire.
Oh God.
I can set the game up myself.
That's some really on board shit right there. I keep seeing ads on my phone, the stupid fucking solitaire games where you play to get cash. I know, I so wanna like, that would be so cool to make the money, but they're like, I made fucking 10,000 this week. And I'm like, so what you're telling me is if I click on this, I'm really downloading a virus to infect my phone. There's no fucking free ticket to paradise here. Like that's drinking the Kool-Aid. I want him, but every time there's like no way. There are games that offer a little bit of money, but it's very, very little, and it's basically because they make enough ad revenue advertising on their own game that they can offer small rewards. But the ones I see with, oh, I moved the ace onto the 2 and at $3 to my account, right? All right. So I don't need to show you guys that. Has everybody used dice before? Like 6-sided dice, cubes. Has anyone not used a little 6-sided cube? Like Yahtzee. Not everybody's, has anyone not played Yahtzee? Okay, you've never played it? A lot, like half of you, the morning class, like everyone said they knew Yahtzee. No, one person, 2 people said they didn't know Yahtzee. Like half of you guys. We'll talk about Yahtzee later. It's like my end game move for today. It's a Hefe end game. Before we get there though, we need to talk about some terminology here. We will use the word experiment. And how do I want to define experiment for you? Experiments are any process where the outcome is uncertain. For example, me asking everyone in the class, what's your favorite ice cream flavor? What's your favorite ice cream flavor would be an experiment. And invariably, I will get the person that can't have ice cream. And then I will feel pity. This ice cream is delicious. I don't know the outcome to anyone's answer to this, so this is an experiment. Not all experiments are like fucking mixing chemicals to do with scientific shit. That's what we think when we think experiment, right? Like trying some science shit out. This is like trying some social science shit out. A trial is running the experiment once. Jackie, what's your favorite ice cream flavor?
Moose tracks.
Moose Tracks. That's not a bad choice. I like it.
I like ice cream, so all of them, but.
But if you were to pick a favorite, you'd go with Moose Tracks. Okay, so Jackie went with Moose Tracks. That's fun. That's a fun answer I don't think I've ever heard, even on any, like I haven't asked this before, like in this context, but even when I've heard ice cream, no one's ever answered Moose Tracks. So I asked one person and I got one answer, so that's a trial. So like if I needed 30 trials, I would have to ask 30 people. That's all trial is. So it's like doing it once. An event is a collection of outcomes. Let me be from a probability experiment. Let me add that in there. So like if I asked 30 people, I would have a variety of answers. Some of them would have chocolate as an ingredient. Some of them chocolate would be the main ingredient. Well, other than the dairy part, of course. But I could say an event is the ice cream contains chocolate. So it can be pretty vague. But it has to capture of the answers, I need to be able to identify which ones are part of the thing. Events should be such that you can identify whether a member should be such that determining if an outcome is part of it is easy. Well, maybe not easy, but doable. Like you might hear some ice cream names and not have any idea what their fucking is. Has anyone not had Moose Tracks ice cream? So you guys have no fucking clue if there's chocolate in it or not. But you could find out if you looked it up. Moose Tracks is like a collection of shit. What else is in it?
It's got peanut butter.
Yeah, there's peanut butter cups, there's chocolate, there's caramel. It's like in vanilla ice cream. There's like ribbons of fudge, I think. It's a nice collection of like, I want all my different candy types in it that aren't fruit flavored.
Has fudge, peanut butter cups, and vanilla ice cream.
That's it. I thought there was caramel in it.
I think there's,
There's like a bunch of different kinds.
yeah, because it depends on which one.
So there's like mint ones that I've had before and. a bunch of different ones.
That sounds immoral. Like you should go to hell if you have peanut butter cups and mint ice cream together. That's my version of hell. That's my version of hell, having flavors that don't go well together. Sorry if I offended anybody there. All right, so those are some definitions to throw at you. There's more, but let me make sure everyone's written that shit down. I like talking religion with people. It's fun. That was interesting to see their viewpoint. I don't grudge anyone their religion, more power to you. The only people's religions I don't like is if you misuse your religion and treat it as a weapon against your fellow man. And there are plenty of people that do that, hopefully no one in here. Then you're just a bad person. And you would be bad without your religion probably. Right? Just use it as an excuse.
When like, did you hear about that killer becoming, like, a Mormon was to kill? Like.
No, that sounds fucking fascinating.
Jeffrey Dahmer. Jeffrey Dahmer.
Wait, hold on. Jeffrey Dahmer's got his own, like, he became a Mormon because he ate people.
Yeah,
He became a Mormon to eat people?
to kill them.
So the eating part is allowed in the Mormon religion?
No, none of that, but he converted just some.
Oh, so he has access to them?
Yeah, get access to them.
Okay, that's different.
To get access.
Doing it for access and doing it to make an excuse for it are two different things. Like, this is a sick version of the similar story, but a pedophile can easily become an elementary school teacher. Just to have easy access. Same type of thing.
Most pedophiles do work in some field of work that has to do with children. Because of that exact reason.
I thought it was for the Catholic Church.
For the most part, it's most of them.
It's access.
Sorry, if you're Catholic, I'm sorry. I worked for them for 7 years. I had to take a shot. They broke me of my religion. Well, they weren't they were the first shove. I don't know if I told you guys about it. I'll tell you about it on break. Let's do some more stuff here. Some more terminology. A key sample space. A sample space, they usually give the letter capital S, which is fucking stupid, because S means sample standard deviation in the rest of statistics. But they give it a capital S, and this is the set of all outcomes. Those of you that were here from 4 to 5, we were talking about sets in there. It's something like that. And I told you what events were, but we usually, For events, we usually use capital letters. To represent what outcomes are in it. To represent the group of outcomes. I'm going to use E and F a lot in this class. Because E goes for event and F just goes for on the next letter of the alphabet. And if I need two different events, I need another capital letter. Probability has rules. Rules of probability. I wonder how many times I'll misspell probability tonight. I fucking mangled it like 3 times in 2 hours this morning. I don't know why. I've spelled it so many damn times. Pardon me, the main reason why I love statistics class is this chapter in specific. I don't gamble a lot, but I love the idea of gambling.
The household.
I have the house always wins. I have done work for a casino. Like contractor work, helping them calculate probabilities of rare events. And I got paid like $125 an hour to do it. Sit on my ass using Excel to do all the fucking calculations for me too. I'm like, I don't want to do this by hand. I need to have an evidence trail. So I did it in Excel where they could see what I did. $125 an hour to sit on my ass in my living room. It was great. That was recently, that was only in the last couple of years. First rule of probability. The probability of an event E occurring. We use capital P to represent that a probability is being calculated, and we put the letter inside of what's being calculated. So that is probability event E. That's how we mark it. It is always between 0 and 1. And it can equal 0 and it can equal 1. How do we get those zeros and ones? The probability of an impossible event is 0. And the probability of a certain or guaranteed event is 1. If there is no other outcome but this, you're got to guarantee you 1. Something fun to know that throughout the rest of this class, the probability of event, if it's less than 0.05, we say that this is unusual. And it's how we identify outliers. You'll see as we go on through the course, but this unusual thing is going to be asked repeatedly throughout this semester in the homework. It's going to do it just constantly. You're going to get fucking tired of it. You're going to go, what the hell was unusual? I know Jones has fucking said it like 18 times and I've done 40 problems with it, but I still got to look it up.
It's say, underneath impossible event.
Certain or guaranteed. So they're always a decimal, like 0.25, 0.19. 0.6432, they're always a decimal. And if we wanted to get probability the way we think of them in terms of percent, we just move the decimal point over twice. So these are always a decimal. Zero point something. But we tend to, as humans, tend to think of them as percents. Our good old percent by moving the decimal point right twice. If the probability of event E is 0.347, it happens 34.7% of the time. In the long term. You can go for a run of 1,000 and have it never fucking happen. Just called bad luck. But it's very much the long term. All of this probability is long term. If you roll a 6-sided die 20 times and you got a 4 or 5, you never rolled a 1. You might think that you can't roll a 1, but that just means you haven't rolled it yet. If you rolled it 1,000,000 times, you will eventually roll the 1 and it'll be about proportional to the rest. We haven't even talked about how to calculate it yet. There's just a lot of definitions in this class, right? This is the premier word problem class in any university. If y'all had known that before you took the class, you may not have taken it. Because no one likes word problems. They're just harder. Because you have to translate the words into math. All right. That was, oh shit, I haven't even done B. That was probably, A was probability of event occurring is between 0 and 1. The other one is, rule number B is the sum of all probabilities equals 1. The sum of all probability they got to add up to 1. As a percentage, 1 is 100%. In fact, we will see a lot of probability models. Probability models are usually tables. Tables of outcomes and their probabilities. Probability models must follow these two rules. To be a probability model. Where is that important to you? There are gonna be questions on like the homework that says like, is this a probability model? And they'll have like a negative number up. Or they'll have a probability that says it's higher than 1. And you go, no. And then they might give you one where the values add up to like 0.97, which is not 1. So it doesn't add up to 1. They might even have one where they give you everything but one value. And they'll say, what does this one value have to be? So that it's a probability model. You just gotta figure out what value goes in there and make it a 1. Lots of events that happen. Anything that doesn't meet these two rules is just a table of numbers and shit. It's not a probability model. All right, finally. Probability of event E, how do we calculate it? It is the frequency for E divided by the total number of trials. So for like our ice cream thing, it's how many answered moose tracks. Well, yeah, I said E had chocolate in it. I'm changing it to, no, let's just leave it at how many answered stuff with chocolate in it over how many people took the survey. Or how many responded. This tends to be for stuff done with something called the stuff done experimentally. And this is called the empirical method. I'll talk about that more in a second. The other way that another formula they do, it does the exact same thing. But it's the number of ways E can occur. Divided by the total number of all possible outcomes. They'll frequently write this as N and E like that over N with S, S being sample set. Or the, yeah, sample set. This tends to go with classical methods. Like dice or cards. And I'll talk about the difference between empirical methods and classical methods in a second. God, I didn't leave a lot of room there. That looks, it's just like a wall of fucking text. Let me put a line there. That at least helps a little bit, right? So you guys have seen stuff like this before. We did this a lot already. This looks identical to relative frequency. they're so close that after we're done with this page, I'll like write down the difference of the two. You'll be able to see the difference when we talk about it both in words. Because people look at them interchangeably and they're not. They're calculated the same way, but they mean different things. Does anyone need this up longer? Right, I see people that look like they're writing. I can't see their hands, but I see eyes looking down and they glance up real quick. And they glance back down and they glance up real quick. And they're looking at that, not the glorious Hefe over here. I had a student yesterday in my algebra class just randomly go, so what do they do when a teacher doesn't show up for a while? What's your first fucking thought right there?
A plan.
Sounds like someone's making a plan to make sure Hefe doesn't come back. I'm like, I'm feeling a fucking, a bunch of people raise their eyes too, like, and the person was on Zoom, so I couldn't see their face. Are you threatening me? What the? No, what do they do? Like if someone's like, if someone's in a car accident, what do they do? I'm like, well, I hope you're not talking about me being in a car accident, but like if they're in a car accident that day, they probably won't get someone to fill in for class that day. But after that, they will have a substitute teacher for the rest of the semester. And the student tried to go, they should just give us all an A. I'm like, you're not here to, I want to make it very, very clear to everyone in this room. You are not here to get an A. You are not here to get an A. You are here to learn statistics. Getting an A is a measure of how much you learn. You're at college to learn, not get a grade. The grade is meaningless to you. You don't give a fuck about the grade. You give a fuck about the job that you're going to get after this education. And good grades tend to lead to good outcomes. But the good grades should be from learning shit. So just getting an A is not beneficial to you. Getting an A like handed to you shows like you mastered something. And if someone hires you based on your mastery of something and you don't know what the fuck you're doing, you can cause some serious harm. Like serious harm, like hurt people.
Look at the job description on the book. Okay.
Right. All right, let's talk about the difference between relative frequency and probability here. Relative frequency is a measure of how often an event occurred. During a unit of time or number of tries. That's relative frequency. Jackie already gave almost an exact description of my next sentence. It's only missing one word. Jackie said probability is the likelihood of an event occurring or something like that. Probability is the likelihood of a future event occurring. It has an unknown outcome. When we do a trial, we don't know the outcome. It's unknown. We'll know what the probability is, but we don't know what the outcome is. On relative frequency, we already know everything. Everything is known because it happened in the past. So there's no give and take on this one. Relative frequency, it's a set number. Unless you ask more people, that relative frequency isn't going to change. I can ask 1,000 people, and if we had that 34.7%, I should get near 34.7% of them, but I may not. It may be like 34, could be 36. But it may be like wildly off, like 44. But it's unlikely to be like 90% if it started at 34. Shit like that. So on the empirical methods, the experimental methods I was talking about, we use the relative frequency to determine the probabilities. But there has to be a large number of trials. I'm going to go over an example of this in a second. The probability for the game Pass the Pigs. Has anybody in here played this game? It's fucking crazy. They fucking sell them. I gotta think Milton Bradley only sells them to fucking teachers to use in stats classes. Because I don't see people doing this. I'll show it to you in a second. That's the empirical method. Classical methods. They have equally likely outcomes. So we don't really need to experiment. Give you a little bit more, and then I'm going to show you Pass the Pigs. I don't know why it's called Pass the Pig. I think the only time you actually pass them is if you lose a round. It should be called Rolling Pigs or some shit like that. You'll see them in a second. Does anyone need this up longer? If you do, raise your hand or say something. All right, let me show you the piggies then. Look at these cute little sons of bitches. The pig has got a dot on their right side and you can't, there's no dot on their left side. They've got two little ears that stick out like fucking like Gizmo on fucking Gremlins. Didn't Gizmo have ears? I don't know. They got nose, stuff like that. They can land one of 6 ways. Someone rolled a sample size of 11,954 pigs. They made sure to get rid of any human interaction by using a standardized surface and a trapdoor rolling device. So you put it in there, and there's a trapdoor, you fucking pull the trapdoor out, and it just rolls out, it's gonna roll. So I'm gonna write these percentages down. Yeah, they roll them damn near 12,000 times. I don't know why they didn't fucking just go to 12,000. They're like, nope, this was just enough.
Probably got tired, but they could be like, you know what?
Right? But why weren't they tired at like 950? Where maybe they just weren't counting it. They counted them at the end. They went until they were tired, and then they're like, all right, how many I got? I've only got 30, maybe I need to do more. All right, pass the pigs. Now you roll the pigs. You score points by how the pigs lands, irrelevant to the point of the conversation. I don't have any fuck clue how to play the game other than I know you roll, and you get points for them. There's 6 ways they land, and this is all about the face-up side. So what is, well, I guess they're not all that way. The first one is the side with the dot is face-up. And the next one is side without dot is up. So the pig could land on either of its sides, and the other side showing. He could land on his back, called a razorback. They have names for it. Landing on your back. There's the trotter. Guess how he lands? He lands on his feet. There's the snouter. Guess how the snouter lands? He's leaning forward on his nose. Fucking back feet are up in the air. His front feet and his nose make 3 points on the that touch the ground. Then there's the one that's just the mythical leaning jowler. This dude is on his nose, one ear, and 1 foot. It looks like he's laying on his cheek, but I don't know that his cheek's actually touching the ground. So after n equals 11,954 trials, the side with dot up is 30.2%. The side without the dot is 34.9%. The razorback is 22.4%. The trotter is 8.8%. The snouter is 3.0%. And the leaning jowler is 0.61%. less than 1%.
Well, like the lower percentage, the higher points they get.
I think so. The less likely it is to happen, the more points you get. And I think if they roll the same way or something like that, that's when you pass them. I don't know, it's not important to that. Like the statistics of where we're going with it. These had to be calculated empirically. Because there's no way we would have just guessed that these were the values. Dice are all equally occurring. Compare this to dice. A six-sided dice. Well, six-sided die. Which is singular for dice. There are 6 outcomes on that. 1, 2, 3, 4, 5, and 6. And the probability of any specific outcome. It's the number of ways an event can occur. Just talked about this over the number in the sample. Like, let's say we're looking for the number 4. There's only one way to roll a 4. And there's 6 different total outcomes. So the probability of any specific outcome on a die is 1/6. We didn't have to do this experimentally to find out. In fact, if you do it experimentally, you're unlikely to get exactly 1/6. You're gonna get really, 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 really close to it. If you roll enough dice. Rolling 30 dice isn't enough. You gotta roll a lot.
Above the word outcome.
Right there,
Yes.
number 4.
Thank you.
Like I was giving an example of an outcome.
Okay.
I'm gonna do stuff with this Pass the Pigs in a second. I want to show you an example of what they do in the homework. And we're gonna use the same idea on these Pass the Pigs. So in the homework, it will ask you shit like this. Probability that someone likes chocolate. Equals, oh, I'm guessing on this one. I have no idea. This would be a fun experiment. I'm guessing it's pretty fucking high. Likes is different than eats. Some people don't eat chocolate but love it. They're trying to have that nice fit figure. There's reasons to not eat chocolate. So not eating isn't the same as not liking. I'm guessing. This was a guess. This is not fact. I just made up a number. In fact, it's probably fucking low. Then the homework will ask you, if you ask 2,000 people, how many can you expect to like chocolate? what they're wanting you to do is manipulate the equation. Probability of E equals N of E over N of S. If you solve that for N of E, the number of times E occurred, you get probability of E times N of S. So this is like saying the number of people that like chocolate equals the probability that they like chocolate times the number of people asked. So this was 0.82. And this was 2,000. If I multiply those, I get 1,640. And they'll probably give you two choices. One choice will be like exactly blank. And the other one is like approximately blank. And you want to do approximately the 1,640. The chances of you asking 2,000 people and getting the exact 2,000 times the percentage is slim. Now you should be close to 1,640. It might be 1,630, 1,659, but it should be somewhere close to 1,640. So you want the approximately route. How does this compare to the what I want to do with Pass the Pigs? Let's see how many leaning jowlers they rolled. I have to do 0.61%, which as a decimal is 0.0061. That's my 0.61%. And I need to multiply it by the 11,954. You're going to get like 72.9 something. So they rolled, I'm going to use LJ for leaning jowlers. The number of leaning jowlers they rolled was probably 73. We could check it. If you divide 73 by 11,954, you get 0.006106. So if I round to 4 decimal places, it is 0.0061. That was 11,954 of them. What if I roll one more? What if I roll one more time and I get a leaning jowler? Leaning jowler. What's the probability of a leaning jowler now? We're basing it on the frequency that's occurred in the past. We had 73, we got one more. So 74 on top. On bottom, we had 11,954 and we're adding one more. So 11,955. And I'm getting 0.006,189. With some more, like even like other large numbers, a lot of large numbers. The 4 decimal places, that is 0.062 or 0.62%. Does that seem like a very big difference to you? 0.61% to 0.62%? What?
1%.
That's not 1%. That's 0.01%.
Oh, yeah.
1%, I would agree. 1% difference is a big difference. It's enough.
Oh,
0.01%. That's like 1% of 1%. That's like the 1%ers of the 1%ers. That's some fucking rich people right there. This actually represents a law. It's called the law of large numbers. And it's crucial to what we do with statistics and probability in general. As the number of trials increases, or grows larger, the proportion of an outcome for an outcome, I should say, approaches the true probability of the outcome. Rolling 100 more pigs really isn't going to change shit. Unless they all landed leaning jollar. But with something that was already like barely 0.5% chance of happening. It doesn't happen often. There's no way 100 tosses is going to get 100 leaning jollars. Unless you've got fucking weighted piggies. All of a sudden you dip one of the ears in fucking lead. How does this affect what we do in statistics? You don't have to ask a fucking million people. You get a good sample from all over the place. You can get away with 10,000 people. And at that point, asking another 100 doesn't change the probability a whole lot. Assuming you have a good sample that reflects the population, and we'll talk about ways of determining like the probability of having a good sample. That's the last half of the semester is like, did we have a good sample or not? You'll never know. You will never know if you have a good sample, but if you ask enough, you got to assume it was a good sample. As long as you did everything randomly, you didn't ask like everybody at the library. One other thing in this section before we go into 5.2, 5.3 is subjective probability. And this is entirely based on personal judgment. Kind of like that 82% I assigned to chocolate earlier. And we usually reserve that for experts. Like economists, when we're deciding if a stock might go up or not. Meteorologists for the weather. I mean, computers do it now, but they give a probability from the computer. But that shit was coded with the expertise of a meteorologist. Let's take a 5-minute break before we continue. I've been going on for a little while. I want to give you guys a chance to. So 5.2 is on the addition rule and complements. Has anyone in here not played this game? If you haven't played this game, the idea is to go around the board and knock the other people out. The game is fucking terrible because most people don't play by the rules. And so it makes the game take like 5 or 6 hours. And when you knock someone out, they're stuck sitting there until the next game fucking starts. If you play by the rules, it's a fucking fast game. I know, I did it. I played it on the computer with my wife. It was like a 45-minute game. It's over. Super quick. They don't give you the option to sell your property and shit like that. No, it's you're out, you're out. All right, so if you're familiar with Monopoly, here's an example. I don't know about your family, but when we play, free parking is a storage for taxes and fees, and it's kind of like hitting the lottery. Land on free parking, you get everything in it. Not every family does it, but most people I've met do. It's like a way to make the game fucking go longer. It's really what it is. If you don't have that in there, it just fucking speeds up the game too. But let's say you're on Electric Avenue and you want to roll an 8 to land on free parking. Or you want to, let me add that right here. You want to either A, roll an 8, or B, roll doubles. Get around the board faster so you can come back around. There's like fucking 6K sitting in that fucking tax thing because no one's hit it. You've been playing for fucking 12 hours. It's a game changer. It's gonna save you from having to sell your last piece of shit hotel. You might slow down the game another 2 hours, but you still won't win because you don't have enough properties. What are the ways we can get these? So A, for rolling an 8, I can roll a 2 with a 6, or I can roll, and I'm using different colors here. I can roll a 6 with a 2. I could do a 3 with a 5, or a 5 with a 3. And if you're using different colored dice, it's a lot easier to see that these are 2 different outcomes. Or we could do 4 and a 4. So that's a total of 5 outcomes. Rolling doubles, I get 1 1. I get 2 2. I get 3 3. 4 4. 5 5. Or 6 6. So here, there's 6 outcomes. There are 36 total possible outcomes. In fact, I'll show you how to calculate that. Where we get the 36 in a couple days, like in our next class. But you can see it, I'll bring that thing back up in a second. You can see it if you look at a set of dice and you just count up the different outcomes. There's 36 outcomes if you counted them up. I'm not gonna waste your time having you count them, they're there. Take my word for it. So I didn't ask what the probability, or so like the probability of getting an 8 is 5 out of 36. The probability of getting doubles, I'm gonna just do DB for doubles, is 6 out of 36. Basing that on the total number of outcomes we found and dividing by the total number of possible outcomes. I'm not simplifying because simplifying is going to make it confusing. It's much easier to leave the outcomes on the bottom as the full number. That wasn't really what we wanted to find out though. We want to know the probability of getting an 8 or doubles. Well, and another way of writing this, if you've seen the union and intersection notation, this is 8 union D. That's a side note. 8 or doubles. Well, let's count it up. Let's look at them. We've got all 5 ways of rolling the 8, right? And then I want to include the 2 1s. I want to include the 2 2s. I want to include the 3 3s. I don't want to include the 4 4s because we already have them from the 8s. I want to include 5 5 and 6 6. That's 5 more outcomes. There is 10 outcomes here out of 36 that give us 8 or doubles. Does that make sense? Not including the 4s again? Because they're already included in the 8s. This is the entire premise of this, of the way this thing works. So if you're not seeing that, say something. We don't want to count them in both groups. Like if I'm counting up the outcomes that work, these 5 outcomes work. All 6 of these work, but the 4 we already counted once. We don't want to count them again. If I count them twice, it's like it would be bad. Well, take a look at this. The probability of an 8 plus the probability of doubles. If we add them, we had 5 over 36 plus 6 over 36. When you add fractions, you just add the tops. If they have the same denominator, the same bottom, this is 11th over 36. It's exactly 1 higher on top. And that 1 higher is from the double 4s. If I just add them both up, I've counted 4 4 twice. I counted it in the 8s and I counted it in the doubles. And we don't want to do that. So we could add something to this. We could subtract the probability of 8 and doubles. There's only one outcome that's this way. The only outcome that's an 8 and a double is the 4-4. And so the probability of that one happening is 1/36. If I subtract the 1/36, I get 10/36, which we know is the correct answer because we counted them. We physically counted the outcomes. This leads me to the next idea, or the general form of this. The general addition rule for probability. A lot of people turned their page right then. That's crazy. People write at different speeds and different sizes. Have that many page turners at the same time? It's not usual. But I can hear it.
That happened.
There was enough of you that I heard it. We say the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. In some books, you'll see it as probability of E union F equals probability of E plus probability of F minus probability of E intersect F. These two mean the same thing. It's usually a wide capital U, it means union. And it means just include stuff for both groups. And the upside down U means intersection. That one is stuff that's only in both groups. It has to be in both to count. That is the worst way of saying intersection. It's the overlap of the groups. But the formula is the important part here. What about rolling at 3 or doubles? Is there any overlap in specific? That's the only thing I'm really asking about right now. No, there's no overlap. The only way to get a 3 is a 1 and a 2, or a 2 and a 1. And neither of those are doubles. When two events have nothing in common, have no outcomes in common, we describe them as two ways. We say they are disjoint, which is the shorter one they use, but they don't use it very often. A lot of times they'll just say mutually exclusive. Each group is excluding the stuff in the other group. When that happens, the probability of E and F, since there's no overlap, is 0. And when you have that, you get what I like to call the shitty addition formula or addition rule. I've never called that before, but I'm going to start calling that from now on. It's the shitty addition rule. It's probability of E or F equals probability of E plus F. And it looks identical to the one up here, but we don't have the minus E and F. Because the minus E and F is 0, and there's no point subtracting. This one only works for mutually exclusive or for disjoint events. And that's why it's shitty. It's like if your car only started on Tuesdays. What kind of piece of shit is that? Right? That would be a weird fucking car. You could actually probably make money with a car like that.
Come see me.
Right, it'd be a fucking circus thing. Come see it, but they'd be like, they show up on Tuesday, they're like, how do we know it doesn't show up or doesn't start on Wednesday? Well, come back tomorrow, we'll show you then. That sounds so scammy,
How do I know you use smart plugs like that?
right?
Check them for yourself. I don't know.
So that's like, yeah, that's really not a good example, but it's a funny example. This top formula works every time. So if you're looking for both, the probability of either one, and you have the probability of these things, probability of each of them individually and probability of both, you're good to go. I see a couple of other heads writing, I assume writing. If you need this up longer, raise your hand real quick. Okay, maybe I was wrong. Next topic in this section was compliments. Not like, oh, you look nice today. That compliment is spelled differently. It's spelled with an I for the first E. The complement of event E and it's denoted E with the C above it. So E complement is the way it's read. Includes all outcomes not in E. So if E is rolling an even number on a die. E complement is rolling odd numbers. This includes 2, 4, 6 on the die, and this one includes all the other options. E and E complement are mutually exclusive. They're like the maximum of mutually exclusive. Everything not in one is in the other. Like rolling a 3 only has 2 outcomes out of 36. Rolling anything but a 3 includes all the other 34. So this leads to the situation that probability of E plus the probability of the complement of E equals 1. Ways this are useful. Variants of this format are, we could say the probability of E complement is 1 minus the probability of E. Or we could say the probability of E equals 1 minus the probability of E complement. In fact, this can actually show you whether two groups are mutually exclusive. If probability of E plus the probability of F equal 1, then F is E complement. As long as E and F are mutually exclusive. I'm going to say disjoint because it takes less writing. That means the same thing. The scenario where this comes up. Let's say we've got 10 guys and 6 girls. And we pick 4 randomly. What is the probability of picking at least one girl? We're not going to do this calculation today, but it does present the idea of it. This is a harder calculation, and we're not even doing it on Tuesday. Well, what are the different outcomes we could have? in terms of girls. We could get 0 girls, 1 girl, 2 girls, 3 girls, or 4 girls. At least 1 girl is all of those. Which means to answer this, we need the probability of 0 plus the probability of 1 plus the probability, not 0. Sorry. We need the probability of 1 plus probability of 2 plus probability of 3 plus probability of all 4 girls. These are not easy calculations. But if I call that event E, what is E complement? The only other option that's in the group. E complement. 0 girls or all boys. And so I can get the probability of E, which is this, adding up all 4 of them, if I just do 1 minus the probability of all boys, which is the complement. And we'll find when we study this topic, this is called a binomial probability. This is a lot easier, like a shit ton easier. Maybe even a metric shit ton. I don't know if there's a difference, but it sounds better to say a metric. Right. I really don't think I'm gonna get through 5.3. It takes about 15 minutes. And we're not gonna get it done today. I was a little more descriptive this evening and this morning. We will do 5.3 on Tuesday.